limit. So what you do is you actually start with the difference in the value of the antiderivative at b minus the antiderivative at a. And you break your interval up into subintervals. So the difference between x1 and x0 is delta x1, and the difference between x2 and x1 is delta x2. So you have these delta x's, which don't have to be the same width. They can be varying widths if you want them to be. And then what you say is that you can then break this up into subintervals. So what you do is you basically subtract the value of the antiderivative at some value slightly less than b, and then you add the same function. So you add and subtract the same number. So I add and subtract, I add and subtract, I add and subtract. And so ultimately it's just basically saying I'm taking I have a picture here, I think. If not, I'll draw you a picture. Oh, okay. I guess I took that off of there, but let me show you what I'm talking about. So if you take this is the plot of not the function but the antiderivative. So this would be capital F of x, which is the antiderivative, and you can evaluate the antiderivative at a, and that would be the antiderivative evaluated at a, and then you can take the antiderivative at b, evaluate the antiderivative at b. That's f of b, and what we're doing here is we're just breaking it up into little changes. But if we sum all the little changes between f of b and f of a, the total difference is still going to be f of b minus f of a. Okay, so that's what these are. This would be f of x sub n would be f of b, and f of x sub n minus 1 would be the value of the antiderivative right here. And that difference, if you take that difference plus that difference plus that difference, add them all up, it gives you the total difference. That's what they're doing there. Okay. So what you do is you group all those terms together. So even I added this and I subtracted it, which is 0. So ultimately, but what you do is then you group this f of x sub n plus 1 minus f of x sub n minus 1. So now we're looking at what that's representing is these little small changes in the value of the antiderivative. So you can create all these pairs, and then if you look at it, what I'm doing is I'm adding up all these little small parts of changes. So it's the summation from I equals 1 to n of f of x sub I minus f of x sub I minus 1. Okay. Now, then we use the mean value theorem. So the question, why did we learn that? And I guess that was why we learned it. When I talked about it, what that said, what the mean value theorem, let me write it on the board. It said if you had a function, let's say we have a function like this, and here's a, here's f of a, and then here's b. And we're just talking about a general function here, and this is f of b. It said that there's some point in here where the instantaneous slope is equal to the average slope. And the way you represent that is you say there's f prime of c, there's some value of c between a and b such that the instantaneous slope, the slope at a given point, is equal to the same as the average slope between the points at the beginning and the end of the interval. So that was the mean value theorem, or intermediate mean value theorem, yeah. Okay, so it's saying this slope, the instantaneous slope here would be lower than the average slope. This one's higher. This one, the average slope is just the difference between the delta y over the delta x, the delta y over the delta x. And there's got to be some value of c in between here where this instantaneous slope is the same as the average slope. What's that? Oh, see me for a minute? Okay.
you notice the heat?
Yeah, that's why we're in here.
Well, you got a little bit more heat.
Yeah, that's.
Ben has moved these classes.
Uh-huh.
See where you at. Math moved you to 651. So here's the option. You can stay here.
Right.
Give them a short class, do out of class, however you want to do it. Or you can move to 651.
Well, what if when we have the body heat? I mean, it's warming up in there.
Well, that's your call.
Okay, that's the option. How long is this going to be?
It could be to 11 o'clock.
Oh, till 11 o'clock? Yeah.
Yeah.
I think we're okay.
Okay.
Yeah. They're giving us an option to move to the armory. How many people is everybody okay with where we are right now? You okay? Got my coat if anybody wants another coat. The problem with the 651 is it doesn't have a, well, I don't know if the equipment works in there. So it's the one next to Mr. Appel's old class. I think we're okay. It's not getting any colder. Okay, so that's the intermediate value theorem, and so you can apply it to these subintervals. So what we can say is that you can see this is the numerator. So the difference between the value of the antiderivative of x sub I minus the value of the antiderivative of x sub I minus 1 is going to be equal to the derivative of the antiderivative, okay, evaluated at some point between x sub I and x sub I minus 1. So this times that difference is delta x sub I. So this part's delta x sub I. This is the derivative of the antiderivative, but the derivative of the antiderivative is just the function. It's small f of x. So this part would end up being f of x. The derivative of the antiderivative is the function. So because of this, because the antiderivative at some intermediate value of c, x equals c, is the actual value of the function, and that delta x sub I is this x sub I minus x sub I minus 1, this part here, the summation of the difference in the antiderivatives, can be replaced with that. And if we take the limit of this as n goes to infinity, it looks like that's the definite integral of the function. That's the definition of the area underneath the curve. So then you can say, therefore, if you let the right-hand side, so the right-hand side is the definition of the definite integral, and therefore we can, I didn't finish it, but the last step is we can say that f of b minus f of a, which are the antiderivatives, is equal to the definite integral from a to b of f of x times dx. Ta-da. Okay, so that's how you prove the fundamental theorem of calculus. Okay, which well, how did I get to this point of never proving the fundamental theorem of calculus? Well, when I first started teaching the class, I haven't taken calculus for a bazillion years, so I'm just trying to get my act together. That's 9 years ago, and then you just kind of keep going on. You make small changes, but you don't go back to the book sometimes and say, "Oh, I've never proved anything." So, thank you for pushing me in that direction. Not that we'll get crazy about derivations, but derivations of theorems. But okay. So chapter 6. So chapter 6 is called differential equations, and you can take a whole semester course, multiple semesters courses on differential equations. So we're just going to be touching the fundamentals of it. And we've actually sort of done that back in chapter 4 when we said y prime was equal to some function of x, and we made y prime into dy dx, multiplied both sides by dx, and then integrated both sides. That was basically solving a differential equation, but we're going to look at some more examples. So the first thing is we're going to look at two approximate methods for solving differential equations. So one is called using slope fields, and one is using Euler's method. You might vaguely remember me talking about Euler's method if you watch the movie Hidden Figures, and they were talking about how to transition from the elliptical orbit solution, analytical solution for the it's not really a satellite. What do you call that thing? It's not a spaceship. Space capsule. So, you've got the elliptical orbit of the space capsule after it's in orbit, and then it has to transition into a parabolic shaped projectile type problem. Trying to get from the elliptical solution to the parabolic solution, the person said we could use Euler's method. So it was a numerical approximation to be able to do that, which you couldn't do analytically. But before we start that, let's just talk about what is a differential equation. And a differential equation is a mathematical equality that involves variables, functions of variables, and the derivatives of those functions. So here is one that should look familiar. Something we've seen something like this before. Y prime is equal to x squared plus x plus 3. So the variables are x and y. X would be the independent variable, y would be the dependent variable. In this case, we have the derivative, y prime, or dy dx. And the function is just is the right-hand side. So you get x squared plus x plus 3. And the question is, in solving a differential equation, is what is y prime? So this equality is satisfied. So I'm not going to go through the individual steps, but if I said a possible solution, so this is my solution, y is equal to x cubed over 3 plus x squared over 2 plus 3x plus c. So all I've done is I've integrated each term on the right-hand side, added the arbitrary constant. If I said, is this the solution? Solution question mark. Well, the way you would solve that is you would say, well, I need to take the derivative of this and see if it's equal to the right-hand side. So if I take the derivative, so if I said, what is the derivative with respect to x of y, which is y prime, and then I do the same thing for the right-hand side. Derivative with respect to x of x cubed over 3 plus x squared over 2 plus 3x plus c. And if I took the derivative, I would get x squared plus x plus 3. So that's the left-hand side. So then you'd ask the question, does x squared plus x plus 3, which is the left-hand side, equal the original right-hand side of my differential equation? And the answer would be yes. And so yes, this is a solution to the differential equation. And the methods to get the solution we've done already. Now, if you look down here, there's another different. This is also a differential equation. Y prime times x plus y double prime times y plus 2 cosine x is equal to 3y e to the y. So again, it satisfies the same requirements. It involves variables, x and y. It involves functions, so things like the cosine of x is a function, e to the y is a function. And it involves derivatives of those functions. You've got the first derivative, dy dx. You've got the second derivative, d squared y dx squared. And the solution would be what is y as a function of x that would make this equality hold. I don't know what the answer is. I just made this up. So, there may be a solution. There may be an analytical solution. There may not be an analytical solution. Now, so one way to try to solve differential equations is just guess and see if it works or not. I could have picked any other function here and taken the derivative, and if that derivative was not equal to the original right-hand side, then it wasn't a solution. So that's a couple of the problems in the beginning of the chapter are, and don't write this down because that's just what I did. So is this a solution to that? The answer is yes. And so let's go to the next one that I haven't already done. So we'll come back to that in a second. So why do we study differential equations? Well, it turns out that we model real world physical phenomenon using differential equations. So you guys who had me for physics, you saw my dissertation and you saw the differential equations that govern fluid flow and conservation of mass, conservation of energy, conservation of momentum. Those are all differential equations, and to find out what the velocity is at every point in the flow field, you have to solve those differential equations, which it's not easy. There's a lot of easier ones that you'd learn before you do that difficult stuff. Okay, so here's another example of verifying that a function is a solution. So here's the differential equation, y prime is equal to 4y. Here's the possible solution. So what we have to do is we have to take this function and plug it into the differential equation and see whether it satisfies the differential equation. So we already have y, so I could plug for y, I could put in c e to the 4x. So the next thing I need to do is I need to figure out what y prime is, so I can plug that in. And so to find y prime, all I do is take the derivative of y with respect to x. So that's the derivative with respect to x of the function c e to the 4x. And that c is a constant, so that would come outside. And then you'd use the chain rule. So the derivative of e to the 4x would be e to the 4x times the derivative of the exponent, which is 4. So y prime in this case is going to be equal to 4c e to the 4x. So now I've got y prime, which I can plug in there, and I've got y, which I can plug in there. And if I do that, I'll get y prime, which is 4c e to the 4x. So that's the y prime is equal to 4 times y. So I take 4 times my y, which was c e to the 4x, and you can see they're the same thing. So yes, y equals c e to the 4x is a solution to the differential equation y prime equals 4y. Okay. Now we can solve this differential equation as well, but we're going to do that later, so I'm trying not to get ahead of myself here. So here's another example. So the differential equation is 2 times x times y divided by x squared minus y squared. And this is is that a solution to the differential equation? X squared plus y squared is equal to c times y. It's not an explicit solution. We haven't solved y as a function of x, so it's probably going to be, I don't know what that thing looks like. It might be like a hyperbola or something. or maybe a parabola, or an ellipse. Might be an ellipse. Anyway, I don't know what it looks like. They're not asking for that. They just want to know whether this is a solution of that equation. So the way you would do that is you would take the original, this function here, take the derivative of that so that you can get y prime and see how that compares with the right-hand side of the equation. You may have to do some additional algebra to prove it's true or not true. So sometimes these involve algebra. But because this one is a implicit equation, I'm going to use implicit differentiation to find what y prime is. So I'm going to say find y prime using implicit differentiation. So what you'd get is you get 2x. So the derivative of x squared would be 2x. The derivative of y squared would be 2y times y prime. And the derivative of c times y would be c times y prime. So we move all the terms that involve y prime to one side, and all the other terms to the other side. We factor out the y prime. So we get that, if I did that correctly. Now first you look at it and you say, well, if I plug that, if that's y prime and I plug it in here, they don't look the same. But they may not look the same because they are, we just haven't done the algebra yet. So just because they originally don't fit doesn't mean they won't fit. This is always the hard part in these, and I don't put one of these on the test, so don't just. So anyway, let's say we'll see what we do. One thing we could do is we could solve for y and stick that in there. So we could solve this equation for y, which would be x squared plus y squared over c. And if you plug that in here, you get 2 times y, which is x squared plus y squared, divided by c minus c. That didn't look any better to me at this point. Let's see what else. Options. That might not be the right option. Let's see if I have it here, because it's always hard, and I never get it right the first time. Because it does work out. Okay, so they are equal to each other. I just got to figure out what I'm doing wrong. It's too early in the semester to run into that. Okay, well, I'll tell you what it is tomorrow while my brain's working a little better. Okay, so that's kind of how those work. I'm trying to decide whether this one's easier. I should just get rid of that one so it doesn't make me look bad. Anyway, we'll come back to that. Let's talk about what the main topics of this section are: slope fields and Euler's method. So these are analytic. These are graphical solutions. So the way the slope field, what you do in the slope field is you plot the direction of the derivative. the slope, at various values of x and y. And so what you end up with is a diagram that consists of arrows, and the arrows they're all the same length. So the value of the derivative, so what we have is a differential equation that says y prime is some function of x and y, and we can plot, so you can, for each value of x and y, you can come up with a number, and that number is the slope, and the slope is the direction of the arrow. So don't think of them as vectors like we do in physics, that they both have both magnitude and direction. These only have direction. And then what you can do is you can start at some initial point. So this is your initial condition. And then you can think of it as, well, the solution has to follow the direction of the arrows, because if I put a curve in there, this curve has to have the same slope at any point as the arrows do in the field. So you can see here I've got these two arrows, so if I took like an average slope of these two between it, this point would be somewhere between these two slopes. And then if I'm going in this direction, this arrow tells me that I keep going in this direction. And then if they tend to curve, say they curve downward ultimately, then the solution curves down ultimately. And so by specifying the initial condition and having this slope field, you can graphically kind of see what the function, the solution has to be based on the slopes. So the way you would solve these problems is you'd have to set up a grid, you'd have to plug in the numbers x and y into the expression for the derivative, and then you would have some initial condition given, and then you'd have to just kind of eyeball it. And let me see if I can find a online app that does this so we don't have to do it. Okay, so what you can do in this this app is you can input the equation for the derivative. So this is f prime of x, y is x plus y. So that's my differential equation. And then at each point, say it's 0, 0, if you plug 0 in, you'll get 0 plus 0, which is 0. So you can see it's a slope of 0. At x equals 1, y equals 0, which is this one, you're going to have 1 plus 0, which is 1, and you can see the slope is 1. The same way here, the slope is 1. And if you do that for all the points, which this computer program does it for you, then you can see the slope field. Now, what this is the solution to that differential equation. So it actually does it does a solution using probably some numerical method other than the slope fields, but it can kind of show you how the actual solution follows the behavior you would expect. So here's your x minimum, y minimum, x max, y max. So that sets how big this function is. And this is the what they've done here is I think they've started at x equals 2, y equals -1, and you can do a numerical solution this way, or you can do a numerical solution backwards and come up with the actual green curve, which is the actual solution, the numerical solution to the differential equation. So let's just put in an equation that we know, kind of know what it looks like. So if we had the equation, let me just write this down on here. So if I gave you the differential equation that y prime is equal to x, the solution to that differential equation, which we can do analytically, what we do is we change y prime into dy dx, We'd multiply both sides by dx. Then we'd integrate. And so we get y is equal to x squared over 2 plus c. So that's my solution to the differential equation. It's going to be a parabola. And depending upon the initial condition, defines what c is. Now if we go to this app and I put in f prime of xy is just x, and I somehow, oh here it did it automatically, you can see the resulting slope field looks like just these lines. Notice they're all the same length. What varies is the direction, or the direction of the arrow. And so let's say I didn't have this green curve in here. I just wanted to find the solution to to this differential equation, y prime equals x, starting here. Well, what I do is I'd say, okay, well, the function's originally going to move along this direction, but you can see as I move to the right in terms of x, it's going to curve. So my solution would curve something like this, and then it would flatten out as it gets to this point. So by the time it goes to the y-axis, it's at zero slope, and then it would follow these streamlines. It's almost like following when you go kayaking. If you've ever gone kayaking and you try to decide where to go, and you can kind of tell where the water is flowing by looking at the ripples on the surface. These are almost like surface. Or if you were doing a wind tunnel and you had little pieces of cloth that you were holding up, and the wind would blow and the little tassels would go in the direction of the airflow. So these kind of had the same representation. So what we have in this case is if you start, let's say we ignore this, and we just say we're going to start here. What's the solution for the differential equation y prime equals x that starts here? Well, again, I'm looking at these arrows, and you can see how now the arrows start to turn. These not arrows, but streamers. So as they turn, the solution has to turn, and you could come up with an estimate of what the solution is to the differential equation. So that's slope fields. The reason I don't give you a problem to do is because, you know, to generate this field, it's 5 by 5. Well, so it's 10 by 10. You'd have to do 100 calculations, which I don't really want you to spend time doing 100 calculations. Here's another one. Let's say f prime is equal to 3y. If we go back to one of the problems that we did earlier, you know, what is the solution to this differential equation, y prime equals 4y? Well, it turns out the solution is y equals c e to the 4x. So we should, if we put in y prime is equal to 3y, we should get an exponential looking function, which it does, except it's going the opposite direction. So what if we put minus? What does that do? So it's like an exponential function, but it's going downward instead of upward. And the reason is because we're starting below the curve. So I think somehow you gotta change the position of the initial point here. I don't know how that happens though. Let's see. Oh, it's probably this. So let's point. That doesn't work. So I think this is a solution depending upon where, because we're trying to go through this point. So there's got to be some way I don't know how you change this coordinate. Oh, there you go. Okay. So if I go through the point x equals 0, y equals 1, then we should be able to get what looks, there we go. So now it works out. Okay, so by forcing it to go through x equals 0, y equals 1, the differential equation y prime is equal to 3y, I get the exponential function. And I forced it to go through here. That actually, this solution is the solution where c is equal to 3, I think. No, that depends upon the slope. This is another initial condition that you have to specify. Again, if you're looking at the slope fields near the axis are 0, and as you get close to this point, then these things would, because I have to go through this point, I can't start moving upward until close to 0 because it moves up very rapidly because of the high slope. And then you can see the slope, the value of the function increases rapidly because these slopes, the slope field is also very high in terms of the derivative value. So that's that. Okay. That's all we're going to talk about slope fields, just kind of the general concept. Okay, the next thing we're going to talk about, which we're going to talk about in more detail, is this Euler's method. So we sort of do the same thing, but we actually come up with, instead of just guessing and drawing a freehand curve, we actually, let me just erase a few things here so you can, as I go through this thing, I'll just describe how it works. Okay. So what you're going to be given in solving a differential equation is you're going to be given an initial condition, just like we did just did in terms of the slope field. You know, we defined a point that we're going through. So we start at that initial value of x, which we call x0, and the initial value of y, which we call y0. And what we're going to do is we're going to evaluate the slope at this point from the differential equation. So y prime is equal to some function of x and y. And we'll assume that this function has that slope for a small increment in x. Now in reality it may have the same slope between here and here, or it may increase or decrease, we don't know. But we're going to assume for this small change in x that the new value of y can be predicted from the value of the slope here. And then what we'll do is we'll get to this next point, and then we'll evaluate the value of the slope at this point, which may or may not be different, and probably will be different, and then we'll use that new slope to then predict what the next value is. And then we'll get to the next point. So theoretically, it's kind of like me. I'm standing here, and somebody says to me, move in a direction 45 degrees for 1 unit in the x direction. So we use our tiles here as my x direction. So I'm just going to say, okay, all I'm doing is moving straight in this direction till I get, oh, there I am on the next tile. Okay, well, what do I do now? And okay, where are you? Oh, well, I'm at x equals 1, y equals 1.6. Okay, the guy plugs the numbers in there. He goes, okay, now move at 52 degrees. Okay, so then I change my direction, and then I move, and I go in a straight line till I get to the next tile, the tile in this direction. And then he says, okay, where are you? At x equals 2, y equals 3.7. Okay, then in the equation, okay, now move at 63 degrees. I move it like that, and then I move here. And so my movement, as I move along to new positions, that's my solution. And, it's not exact because the slope changes between the original position and the new position. But if I make my delta x as my change in the x value small enough, it's pretty close. It doesn't change that much. And so my solution is actually pretty decent. Okay, so let me demonstrate that here again. So what I did is I said, what's my slope at this point? So the slope that I'm using here is what is the slope value at x0, y0, my initial condition. So then I use that slope, and I say, okay, if I move to a new value of x1, what is my new value? My new value here. That's my y1 value. and I'm getting y1 by just assuming I'm moving linearly from here to here. Now at this point, I can now come up with a new slope. So what I'll do is I will calculate f prime at x1, y1, and let's say that's a little bit steeper. So then I will go, and so then I'll move certain distance in the x direction, same increment. I'll use this slope, my new updated slope, to then figure out what my y value is here, and you just continue on in that method. So let me just demonstrate how it works. So let's say we want to start, here my differential equation is y prime is equal to x plus y, and we're going to start, my initial condition is x equals 2, y equals 1. So we need to make up a table, and the table is going to have the x value, the y value, the value of the derivative, and then my, I'll call it x, we'll call this x1, we'll call this x2, y1, y2. Okay, so that's good. So I need five columns and make it 5 rows right now. Oops. Okay, so x1 was 2, y1 was 1. So what we can say is y prime at 2 comma 1 is going to be 2, which is x, plus 1, which is y, is 3. So y prime is 3. Now the question is, how do I predict the new value? So the way you do that is you say y prime is equal to y2 minus y1 over x2 minus x1. We just use the equation for the slope of the line. So what we can then, if you solve for y2 is equal to y1 plus y prime times x2 minus x1. So that's how I'm going to calculate y2. I'm going to specify x, so x2 is going to be 2.1. I'm going to increment it by 1/10. So let me add a page here. So what I can say is x2 minus x1, which I'm going to call delta x, is 0.2. I mean, it's 0.1. It's 2.1 minus 2. So that's my increment. Then I can calculate y2. y2 is equal to y1 plus y prime times x2 minus x1. y1 is equal to 1 from here. Y prime is equal to 3 from the equation for the derivative times delta x, which is 0.1. So that's going to be 1.3. 3 times 0.1 is 0.3. So my new value of y is 1.3. And then what I can do is make x2 equal, just start over again. So those new values of x and y are now my O values, and I'll do the same thing. So what you will do is you'll calculate y prime not at 2 comma 1, but at 2.1 comma 1.3. So what I get is I get 2.1, which is x, plus 1.3, which is y, which is 3.4. So that's my slope. So you can see it's getting bigger. It's not the same. It's changed. So my new x2 is just going to be this plus 0.1. So I increment it again the same amount. So I'm moving in the x direction by 0.1 units. And then I can calculate y2 is going to be equal to y1, which is now 1.3, plus my new slope, which is 3.4 times my difference in x, which is the same, 0.1. I keep that increment the same. So I get 1.3 plus 3.4 times 0.1, and I'll get 1.64. So that's my new value, 1.64. And then I copied those down again over here. And you just keep going on. So go ahead and see if you can calculate the next value here. So this is going to be 2.3. That's easy. So you need to calculate the slope, which is actually just these two numbers added together. So you get your updated slope, and then you can calculate your new y2 value using this is y, this is y1, this is your slope times 0.1, and you'll get something. It should be, this is 1.3, 1.64. It's probably going to be 1.9 something. Just thinking about how it's changing. So this one's going to be 3.84. This is 2.3. So I got, it's actually a little more than 1.9 something. Went to the next one, 2.024. So this is this plus that is that from the differential equation. And then if you take this value plus that times 0.1, you'll get 2.024. And you just keep on like that. So what you have now is you'll end up with x values versus y values. And let's go back to that slope field thing. That's how they came up with that solution. They may not have used Euler's method, but they used some method. So if we go back and we change this differential equation to x plus y, and we go through the point 2, 1, like that. So all we've done so far is we've just done this little part of we've gone from here to about there. We've gotten 3 points that we can use to fill that in. And if we kept doing it, we would continue on in this direction. And that's how you get the green curve. Now there are other ways you can make this a little more accurate. What you would do is you would first calculate the slope here, then you would find the new estimated value, calculate the slope there, and then use the average of these two slopes to do the calculation over again. It's called a predictor-corrector method. So what you do is you predict where the next point is, use that next point to get a new slope, but then correct the slope that you used originally to make a second estimate of the point that you're going incrementing. And you would do that through each step. So you've got to go through twice as you predict the new slope and the new point, and then correct its position. And then there's a whole slew of other techniques to use to give you, it's a more complicated algorithm, but it gives you a better prediction. So that's one way of improving the accuracy of these numerical solutions. The other one is if you increment it in x 0.01. instead of 0.1. So if you decreased this change, then over that small change of 0.01 instead of 0.1, the slope is going to be fairly constant, and that gives you a better solution. So there's two ways of improving accuracy. One is to have a finer finer change in x, and the other one is to use other methods that we're not going to talk about. So that's Euler's method. I'm going to go ahead and assign homework from this section for next, since we give you a week to do this. We'll talk more about it next time, but it's problems. There you go. You can see what the problems are. 20, 23, 33, 39, 42, 71, and 80. That's due next Monday. So we'll see you, most of you, in 15 minutes. You can go over to the Moomaw Center and warm up a little bit. Come back here. We'll start a fire, a little campfire.